hypothetical bytes in them. So that's why this event is parameterized on this byte type. You can think of it just as bytes. And so an event can either be a connection happening, something going to the server, or something coming back from the server. And now a trace is just a list of events. Okay, now we have real ones that are events parameterized by real bytes, and we have hypothetical ones that are events parameterized by hypothetical bytes. And now here is the interesting part. We have is_server trace, which is a relation between servers, which live in the server M monad, which is M applied to server E, and traces. So this is the relation that says, given a server, what are the traces that it can generate? And then similarly, is_observer trace says, is this hypothetical trace a trace that's accepted by this observer? Good, let's see some examples. So here are some examples. So first, remember the server loop. Maybe the notation makes more sense now. So the swap observer loop is an interaction tree with a disjunction at the root, an OR node at the root. And on one side, it has a connect and then just loops back with C added to the list of connections. And on this side, it chooses a connection. Choose again is going to result in some OR nodes in the tree. Then it observes a message being sent to the server on that connection, and observes a message coming back from the server, and checks that that message is the last message that was being sent. So this obs message from server is observing things coming back and checking that they are what they should be, and failing if not. And then it loops back. Okay, so this is the top level spec. And now let me just introduce some notations up here. So what I want is to show you some examples of traces. And so this, for example, is a trace of the server that we just saw. And it looks like this. And the notation looks like, so number bang is a connection being accepted. And arrow in this direction is a message coming from the world to the server. So we're observing a message going into the server. And in this direction, we're observing a message coming out of the server. So this trace looks like two connections got accepted. And then on connection 0, 3 bytes went into the server, ABC, and then 3 bytes came out of the server, 0, 0, 0. Since the initial message that we initialized it with was 0, 0, 0, and since the buffer size was 3, that's a single correct loop through the server. Well, it's 2 loops through the server loop. It's 3 loops through the server loop. 1 to open this connection, 1 to open this connection, and 1 to do this exchange of messages. And then 1 more trip through the server loop says the trace D comes on connection 1, and then E, and then F, and then the event observe an output from the server on connection 1 with the bytes ABC. So we're seeing the bytes here that we sent here. And that means this server is behaving correctly. The behaving correctly part I'm going to come back to in a minute. We need to talk about scrambling and stuff. At the moment, I'm just pointing out that this is a trace that can come out of the swap server definition that we saw. And here's another trace that does not come out of it. So if we send ABC and then observe 1 coming back, that's wrong. Okay, so this isObserverTrace test is just a Boolean function that is computing the isObserverTrace relation that we were looking at a minute ago. Okay, now let's go back here. Now we need to talk about descrambling. I don't have too much time, but I'm going to try to give you the intuition. The intuition is in between the actual server and the observer that's saying whether it's good is a network. What does the network do? It allows connections to be opened, and then on those connections, bytes can be inserted on one side and taken off on the other side, and then since connections are bidirectional, bytes can be inserted on the other side and they can come off the first side. So the state of a connection is it starts in the closed state, and then when a client initiates something, it turns into a pending state, and then the server has to accept it. It goes to an accepted state. So there's a little state machine where these are the 3 states, and then so we can represent the state of each connection by one of those 3 things, and then a list of bytes going in each direction. And then the initial state of the network is all the connections are closed. And then we can define a notion of a transition of the network. So a transition of the network takes a state that we're in at the moment, and it either fails, it says that transition is not possible, or it says that transition is possible, and we return a new state of the network and a byte that came out. A byte or a connection ID, maybe. And now we have, there are 6 actual transitions. A transition that says server accepts, which takes a network where there's a connection that wants to be opened and turns it into an open connection, and so on. Server send takes a network in which that connection is open and turns it into a network in which there's one more byte on that connection. So this transition relation defines a state machine, essentially, that defines the possible behaviors of the network. And now, we can define what it means for a real trace, for 2 real traces, excuse me, to be related by a network that's in this state. In other words, given an initial state of the network that looks like this, it is possible for the endpoints to observe these traces. And looking down a little bit, this gives us our top-level notion of correctness. So remember in the top-level theorem, the first line said refines mod network. And refines mod network says, for every real trace of the server, and every real trace that is a possible scrambling of that server trace viewed from the other side of the network, there exists a descrambled version that is a trace of the observer. In other words, the observer is defining, the observer is a very simple kind of linear description of what's the right way to say it? The intuition is the same as in discussions about linearizability in databases, where you say the specification of correct behavior assumes that things are arriving at the server in a simplified kind of linear form. What can actually be happening out in the world is all sorts of scramblings of that that are induced by the network. But the behavior of the server is okay as long as it can be interpreted as long as it can be descrambled into something that can be accepted by this simple linear specification. Okay. And then, so that is a logical thing, a proposition. We can also define a similar thing that is a checker, that actually takes an observer tree and a server tree and checks whether all of the behaviors of the server can be descrambled into behaviors allowed by the observer. Okay. So, let's see some examples of that. So for instance, here is a particular trace of the server, and here is its descrambling. This is a particularly simple example because this trace of the server was not scrambled. So so this trace of the observer was intuitively passed through the network without messing it up. And we can see immediately that it is a legal descrambled trace because the observer accepts it, where the observer is the spec that we started out with. Okay, but here is a more interesting case where the actual observation that we made on the observing or testing side was we saw two connections opened, then we saw some bytes going into the server on connection 0, and then we saw some more bytes going into the server on connection 1. And then we saw some bytes coming back on connection 1, and only at the end do we see the initial message coming back on connection 0. But that's fine because all of this can be descrambled. That is, we can hypothesize a behavior of the network or an order in which things happened on the network that gives us this descrambled trace. Okay, here is a bad trace. So here's a trace where we sent the server ABC and it sent us back X. And this is bad because under no descrambling is it possible for messages to just get made up out of thin air. So this X was not a value that anybody ever sent the server, and it's just not allowed to send it back. Here is a more interesting bad trace where, so along connection 0, we send it ABC. Along connection 1, we send it DEF. Along connection 2, we send it GHI. And now connections 1 and 2 see each other's results. Right, so on connection 1, we see the stuff that was sent on 2. And on connection 2, we see the stuff that was sent on 1. And you have to ask yourself, if this were a possible trace, then how would we explain it? That is, would we guess that the communication on connection 1 was received first, or the communication on connection 2? And neither way works, because if the communication on connection 1 was received first, then what should come back on connection 1 should be ABC, not GHI, and vice versa. So there's kind of a causal loop here. And the result of the causal loop is that there's no explanation of this that can be found by descrambling. Okay, and now finally, let me show you why we have these hypothetical things. So here's a trace that we saw, and here's an explanation of it. But to give an explanation of it, we have to assume that there are some results coming back on connection 1 that we haven't seen yet. So what did we see? We saw 2 connections getting opened. ABC went to the server on connection 0, and then DEF went to the server on connection 1. And now what came back on connection 0 was DEF. So what does that mean? That means that the server must have gotten the messages on connection 1 first, and then the messages on connection 0. And so there must be some messages coming back on connection 1 that are delayed in the network. It's important to put these here because this is the only way we can explain the rest of the behavior, because remember the specification is simple, it's linear. So when the specification accepts some things, some bytes from the outside world, it immediately sends the last message that it remembered. So we need these hypothetical things in order to interpret what happened next in terms of this linear server. And in particular, the reason we want to do this is that this allows us to reject event sequences that look very much like the previous one, except that, for example, it receives an X which was never sent to it along one of the channels. Okay, so these are some examples of specific traces that are or are not accepted modulo scrambling from the network by the socket spec that we wrote down. I'm going to take some questions, and then I'm going to show you some examples of server implementations that either do or do not refine the server spec modulo scrambling. Question?
Is there typically only one good scrambling, or does it not matter if there's more than one?
I think there could be more than one. Probably depends on exactly what the spec says. Yeah, sure. You must be able to do more than one, because, for example, you could put the two connects in either order. It doesn't matter. Yes.
We define the observation, only the observation from the server to the client as being an option by. Why couldn't we say the same thing that the client sends